Okay, so one of the most painful things of sled riding ever is you get to the bottom of the giant hill and you have to climb back up to the top. And I remember when I was a little kid, really young, I barely remember this. I had a radio flyer sled. It's the ones where you go down head first and it's got like a steering column at the top. And I remember my grandfather, Grandpappy Botzer, he said, if you get out of control or you need to bail, just roll off the sled. And I went, yep, I can do that. And went to the top of this ginormous hill and I was flying down it and I totally lost control, but I didn't bail. And I went underneath a fence and ran into hay bales at the end of it. Oh boy, I was crying all day. But anyways, if you walking to the top of that hill is a pain in the butt. It would be really nice and really brilliant if we put a pulley system at the top of the hill so that one person could slide down it and pull another person up. And then when the other person's at the top of the hill, they'd go down and then you get pulled up. And you could just sled the whole day. It'd just be like perpetual sledding forever. It'd be awesome. So we have set that problem up. Um, After pulling you up the hills all day, your friends become tired. So to never do that again, we've created an ideal pulley system at the top of the hill, as seen in the picture. And it's an ideal pulley. It has no mass. We don't have to worry about rotational inertias or anything like that. And if you're watching this or you're here live right now and you're like, what's a rotational inertia? Don't worry about it. We'll come back to it later. But it's a perfect pulley, okay? So when your friend, who's at the top with a mass of 82 kilograms, goes down the hill, they're going to pull you up. So what we'd like to figure out is, since this is a connected object system, we have a perfect rope here. It's not going to stretch or be a spring or anything like that. Since it's a perfect connected object system and our accelerations are the same, what is the accelerations of the sled and what's the tension in the rope? Because if these accelerations aren't thrilling enough for us, maybe we won't enjoy sledding. So let's actually figure this out. So the first thing we can do is, while we have a wonderful picture here kind of showing things to us, a free body diagram is just a little bit nicer. And since this is on a frictionless surface, we are not going to concern ourselves with the weight perpendicular or the normal force. Remember, the only reason we need weight perpendicular is to define a normal force, and the only reason we need a normal force is because friction is fun. But we don't have friction on this wonderfully snowy surface, so we're not going to bother with our into the hill and out of the hill forces, these perpendicular normals. All we need to concern ourselves with are the forces going down the plane and back up the plane. So first, let's draw ourselves. Here we are on the left side of the hill, and what's going to pull us up the hill is a tension, and what is trying to pull us back down the hill, well, that's our own weight, or rather a component of it. And while the free body diagram has our weight pulling down here, what we are really concerned about is the parallel component. So while this is actually the free body diagram for us on the left, and if we draw the right real quick, their weight is acting down as well, and they have a tension pulling them back up the hill. Oftentimes, to kind of save us a headache, while this is the free body diagram, physicists, in an effort to be as lazy as possible, we sometimes cheese this. And what we might do is we might accidentally put an arrow here. That's not actually a free body diagram arrow, remember, because this is the parallel component of the weight. So it doesn't actually belong in our free body diagram. But in an effort to save us some headache, let's just recognize that, hey, we need this weight vector. We need the amount of weight acting down the hill, that parallel component, which we recall is mg sine of theta acts down the plane. And that means over here, likewise, there is some parallel weight component acting down the plane for our friend, which is mg sine of theta as well. And we just have to remember that we have different masses, and gravity is gravity. G is that classic 9.8 meters per second squared. So looking at this here, we have our forces. We've got our parallel component down the plane and a tension, and we have a tension and a parallel component down the plane. And with these forces, we just need to quickly say what's positive and what's negative, and then set up our F equals ma equations, and we'll be set. So this is kind of weird because we've got two inclines. How do we set up positive and negatives? How are we tilting our head here? Well, what I like to do is I like to choose the direction of motion to be positive. And we've done this before. So let's say going up the plane is positive, but then as we roll over the pulley, we're still going in that forward direction. So then down the plane on the other side becomes positive. So for ourselves on the left, going up is positive and going down is negative. But for our friend on the right, if we continue that motion, going down is positive and going up is negative. So that means our tension will be positive, our weight parallel will be negative, and on the other side, our weight parallel will be positive and our tension will be negative. And this also works out very well because these tensions are equal, but they are opposite. One is positive, one is negative. That's defining Newton's third law. If these tensions are both positive or both negative, you done goofed, and you need to fix that, okay? So now that we've got our diagrams, we've set our positive and negatives. Let's just set up our two F equals ma equations. For ourselves on the left, we have a positive tension, so tension, minus some parallel weight. So this is minus because it's acting down the plane. This is our weight parallel. It's the mg sine theta. And if we put in our values here, our weight, or our mass rather, was 68 kilograms times 9.8 to get our weight, and then multiplied by the sine of the angle of this inclined plane, which is 30 degrees. And if we know anything about unit circles, sine of 30 is 1/2. So that's a nice thing there. And let me redraw that 8 because it kind of looks like a 0. Whoop. Okay, and this will have to equal ma because, as always, we are just saying the sum of the forces equals ma, Newton's second law. So this will equal our mass, 68, times an acceleration. For our friend on the right side of the board, or the mountain rather, we're going to have a very similar equation, but this time they have a parallel component going down the plane, so it's going to be mg sine theta comes first. Their mass was 82 kilograms times 9.8 times sine of 30, which will be 1/2, minus the tension acting back up the plane, and that will equal ma. That will equal 82 multiplied by a here, okay? And at this point, this is a system of equations. There's many ways to solve it. However you like to, you can totally do that. The way that I like to do this is I like to add the equations together because I have them set up so that all my forces are on the left, all of my accelerations are on the right. So in doing that, we quickly see that these tensions are equal and opposites. So these tensions can go away, they can go whack, whack. And what we're left with is just the red parallel component and the blue parallel component. And if we write that out, let's actually just get a number here for the red one. So that's 82 times 9.8 times sine of 30, which is just 1/2. So we get 401.8 newtons, and then minus, because there's a minus sign right here on this number. Let's figure out that number, 68 times 9.8 times sine of 30. This in blue, that component is 333.2, and these are both newtons, equals. And then here, since these are both the same acceleration, we can add the like terms together. 68 and 82 gives us 150 kilograms multiplied by an acceleration. And in this way, we can solve for the acceleration now. This isn't too bad. Let's subtract our forces on the left. 401.8 minus 333.2. That'll give us on the left-hand side here a total force of 68.6 newtons. That equals 150 kilograms times an acceleration. And you're probably seeing where we're going with this. We divide by the 150. And 68.6 divided by 150 gives us an acceleration of 0.46 meters per second squared. Okay, so nothing too crazy there to find our acceleration. We've done a lot of problems like this to kind of solve that out. Now, before we go and find that tension, and we're going to find it, very basically by taking this acceleration and throwing it back into one of these two equations. It doesn't matter which one you pick. You just got to throw it back in to solve for t. What some of you may have recognized was instead of drawing 2 free body diagrams, what if we just drew one large system here? What if we took everything as one? Well, that is actually what we did when we added these equations together. If you pretended that everything was 1 here, you would just have your friend's force pulling you down. So the 401.8 minus tension, because that tension's pulling them back, and then plus tension pulling you forward, and then minus your force pulling you back, the 333.2. And since that's the entire system you looked at, it'd be the total mass, which is 150 multiplied by an acceleration. And if you did it that way, if you looked at the whole thing as a system, you once again see the tensions go away, and this right here is the same equation as this down here. So if you want to write it in 2 equations like we did, the left and the right person, or if you want to write it as a system, both will give you an acceleration. I like writing it like this with the left and rights because now that we have an acceleration, we've already written an equation to allow us get us back at tension. So let's go ahead and use a tension equation in order to solve for that tension there. So if we do that, our equation for tension minus the 333.2, because that is the mg sine theta for you, and that will equal 68 times 0.46. And at this point, it's just some multiplication and addition. The 68 and 0.46 is going to equal 31.28. And then we're going to add a 332 over to the other side. So when we add the 333.2, we get a total tension of 364.48 or some rounding newtons because that is a force. Okay, so however you like to set up and go through that problem, it's really up to you. The key thing is that, hey, we had a picture. We drew wonderful free body diagrams up here. These free body diagrams are the most important thing because as soon as you draw them and you have them in our setup, you can create your equations. And then at that point, it's just a little bit of math to solve things out. And we've done this kind of math where we combine equations a number of times now. We've looked at this problem, the problem in the notes. We've looked at connected objects with the mouse and the cheese, the pulley problems, the truck and the camper. Like, we have seen these things before. Blocks pushing on each other. There's a lot of connected object stuff that we've done. This is just one more extension of that. So nothing too crazy. But with that, this is a good time to go sledding. Except, maybe that acceleration is a little slow. Maybe we want a little bit more speed and we got to get a steeper hill. But this is finished. So adios and take it easy.